Hey there, everybody. It's 2022, and these are the official start of Calc 2 videos. All the other videos so far have been just review from Calc 1, but this is where it starts for real. So we're going to jump right in and get started on Chapter 5, which is Applications of Integration, and we're going to talk about areas between curves. And this stuff starts off fairly simple the way you would expect it to, but as you will see, there's a lot of applications and some of them are unexpected. So we'll be building, as we progress through Chapter 5, it'll all be building pretty heavily. So the idea here is, let me move my big face out of the way. Yeah, that's pretty good, I guess. So let's say we have this region here. So the idea is, how do we do an integral if there are two functions and we want to find the area between? So you can see this blue region S is the area between. We know from Calc 1 that we would be allowed to just find the area of one of these and subtract the area of the other. But that's not going to be good enough for the things we're going to be doing in future sections. So instead, we're going to define a new technique. For all intents and purposes, it looks just the same as a normal integral, but you do have to make sure when you set the problems up that you do a few things in a particular way. So same thing we saw with ordinary integration. We have a and b; those are points on the x-axis, and we call them vertical lines, but they could just be points, as you'll see in some future problems. And the idea is we just want to find the area between the curves. So we will end up subtracting the functions, as you will see. The only thing you need to note is that for this formula to work, f of x has to be greater than g of x. They're not allowed to cross. Later in this video, we will see that they can cross, but we need a new technique for that. So here's a review of what you learned in Calc 1. We saw how to divide S, that's our area, that's the region, into n strips of equal width. And that's what this is showing here. So here's one strip. We call it a typical rectangle. I'll be using that phrasing in a lot of future sections in Calc 2, typical rectangle. And the idea is that if you just pick any strip, that's why we call it typical, it doesn't matter which one you pick, that it's a rectangle, and the height of the rectangle is given by the function here. So what we're doing is, I don't know if you recall this from Calc 1, but the way it works is the star notation means that it's any point in the interval. And what we do is we have the function cross the rectangle at some point in the interval. It doesn't matter where the crossing is, because we're going to end up taking the limit as n goes to infinity, which will compress the rectangles. So it doesn't matter where in the rectangle that we pick this point to be. So that's why it's called xi star. The star just means any point. It's called a sample point. And the base of the rectangle is delta x. And delta x we saw in Calc 1 was just b minus a divided by n. And you can see it here, right? So here there's 9 rectangles. So the width of each of these rectangles would be b minus a, whatever those numbers are, divided by 9. So each rectangle is the same width. And that gives us a Riemann sum. And it looks pretty similar to what you saw in Calc 1. And keep in mind, we are leading with our intuition here. There are proofs of all of these formulas. I'm not going to prove any of this stuff. It is very similar to the Calc 1 version of areas, so there's no need to go through all of that again. If you're interested in the proofs, contact me, and I can show you where in the book that stuff's located. Okay, so yeah, so that's the idea, that the height of the rectangle is f of xi star here, so this function at some point, and then this function at some point. You subtract it to get a height, right? And then you multiply by delta x. So that's the width of one rectangle. Sorry, this is the width, this is the height. So it's the area of one rectangle, and you sum all the rectangles. And we just want to eventually take the limit as n goes to infinity, right? So it makes sense that as we increase the number of rectangles, that the sum of the rectangles will get closer and closer to the true area between the curves. Again, this is the same argument that we used in Calc 1. And so it turns out that this thing right here is exactly the definite integral. Because remember from Calc 1 that when you have a sum, you can split a sum into two different parts. So you would have this sum minus, and you would distribute this sum over here. Well, those are both definite integrals. And then you would combine them back together again. And that's what we do on the next slide. Right? It's just this here. So this is the formula for the areas between curves. Notice here there's a vertical line on the left side. Here it's a point. It doesn't matter. But they're not allowed to cross inside the interval. They can touch, they can't cross. Right? They're allowed to be equal, but f of x has to be greater than or equal to. Yeah, so we have two functions, a left and right endpoint, and all we do is you just subtract the functions and do the integral. Or if it's easier, you can distribute the integral through the minus sign and compute them as separate integrals. It's up to you. Generally speaking, I'm going to be doing this. There are problems on the homework where you have to draw the graphs. And on a test or something, you may be asked to draw these graphs by hand. I mean, you'll still graph them on your calculator and then just like sketch them by hand. If that happens, sometimes it's easier to use this method because you can see both curves. When you combine it like this, you're kind of just mixing the two graphs together. And so when you graph it, it doesn't look the same. You'll see that on the homework. But you always want to graph the functions separately. So here's an example. This is a homework problem, obviously. And it says find the area of the shaded region. So we're going to use what we developed before, which is it's just going to be this top function minus the bottom function. And you really want to draw that typical rectangle. At this point, it might not be clear why you want to do it, but as we progress through this chapter, you will see that there's going to be lots of techniques, and they all require drawing some sort of rectangle. So what we do is we find the integral of the top function minus the bottom function over the region. Right? I just talked about that on the previous slide. You can see when you graph it which one's the top function. If you were just looking at these two functions on a piece of paper, you might not know which one was the top function. So the graph helps you decide which one is on top and which one's on bottom. And so all I'm doing is I'm just subtracting the two functions here. So we need to find the integral of the difference between these two. All I'm doing is using the formula from 2 slides ago, and I put it in brackets just so you recognize it. So I'm just taking that function minus that function right here. So there's the top function, there's the bottom. Subtract, simplify. So this is the integral I'm going to take. So if you graph this, it doesn't look like that, right? You need to graph both functions separately to see what it looks like. Also, the graph is very helpful for finding the intersection points. You can use algebra or you can use a graph to find intersection points. Here we were given the graph for this problem, so I'm just using the graph. In future problems, we'll be solving for the intersection points if we have to graph it by hand. Right, we saw from the graph the intersection points are 0, 0, 6, 12. Now we're interested in the x values of these intersection points. So our limits of integration are going to be x equals 0 and x equals 6. Right there, 0 to 6. And then the area, you just take the integral of the difference between the functions. So we've already done that subtraction problem, right? So f of x minus g of x, we've already simplified as this. If it's easier for you to leave them separate, you're allowed to do it that way too, but that's not normally how I do it. And obviously you guys know how to do integrals, at least polynomial integrals. And plug everything in just like an ordinary like Calc 1 problem. You get 36, and that's the right answer. So we're actually going to come back and revisit this problem at the end of the slideshow. I'm going to show you guys how to do definite integrals on a graphing calculator. And so this is the problem that we're going to be doing. I'm just going to show you how to like just do this slide on a graphing calculator without doing any arithmetic. And that's where we're headed in this class. And when I had the one-on-one meetings with some students, I talked about it a little bit. that most of what I'm interested in is this stuff. Can you draw the graph, find the intersection point, set up the graph, set up the integral? Can you get it to being a definite integral? Can you get it to this stage? That's what I'm interested in. From here, it's not a Calc 1 class. Okay, so that's the end of example 1. Now we're going to see some different takes on this. So it turns out that you don't have to just integrate along the x-axis. The functions could be functions of y, where x equals a function of y. So here, x equals f of y, x equals g of y. And there will be horizontal lines that are the vertical bounds. And if this happens, the rightmost function has to be greater than the leftmost, right here. And of course, y has to be between the endpoints. When that happens, all we do is we just flip the bounds of integration. So instead of going in the x direction, we're going in the y direction. It doesn't change anything. It just sometimes you're given curves that geometrically you'd rather integrate in the y direction because maybe it looks like this, and maybe the curve is not a function of x. And so that's one twist, and we'll see how to do some of these. There's one more twist that happens early in chapter 5, and we're going to see that pretty soon. So find the area of the region enclosed by x equals 2y squared and x equals 4 plus y squared. So just looking at it, you don't know which one's on the right, which one's on the left. So that's something that you have to figure out how to do, and your graphing calculator will not graph sideways functions. So I drew the graph in Desmos. You can type in x equals 2y squared, x equals 4 plus y squared, and then you can kind of zoom around and see how it goes. And if you make the graph look nice, you can see the intersection points as well. If you'd rather graph the function by hand by plotting points, that's fine too. I'm not going to have you graph any of these sideways functions by hand on a test, don't worry. But when you're doing the homework, you have access to the internet, obviously. And you would just type it in exactly the way it looks. X equals 2y squared, x equals 4 plus y squared. And Desmos is very easy to use if you haven't seen it yet. So what I need to do is subtract the leftmost function from the rightmost function, because the one on the right is above. It's higher. The numbers, the values are higher, so I need to subtract. So just like when we integrate with respect to x, it's top minus bottom. When we integrate with respect to y, it's right minus left. So you could see from the graph the intersection points were -2 and 2, but there's no guarantee that any given graph will have nice intersection points. So the way to do it is you substitute one equation into the other and solve. This is a very easy problem to solve. It factors real nice. We already know that it's -2 and 2. So those are your bounds of integration. Again, even when you're going in the y direction, you still put the lower number on the bottom, and then you evaluate the integral. So again, here's the formula, right? We know the bounds, and then we're going to take the rightmost function and subtract the left. There's the rightmost function, there's the left. Turns out I already did that subtraction up here when I substituted one equation into the other. That happens sometimes. When you're solving these, though, you don't always get the same thing because you might have them switched when you're solving. In this case, it is the same. So it's 4 minus y squared. Another very easy integral to do. Plug the numbers in, and you get 32/3. So we've seen integrals with respect to x, integrals with respect to y, and now one more twist. So sometimes the curves cross, and as I mentioned earlier, you need to use a different technique. And the way that I put it in the notes is you're asked to find the area between the curves f and g, where f of x is greater than or equal to g of x for some values of x, but g of x is greater than f of x for other values of x. Wherever it crosses, you have to split the integral into multiple regions. Each region will have its own area, and then we're going to define the area of the region S. So the overall area between the curves is the sum of the individual areas. The reason we have to do it this way is that by definition, all areas are positive. We never really have a negative area. In Calc 1, when we have a negative number in front of an area, like an area that's below the x-axis, it's called a signed area, and you learned about that in Calc 1. Anything below the x-axis, the area is still positive, but you just put a negative sign in front of it. So there's no such thing as negative area. And you can see that here, right? So, because if you just did the integral from a to b of this function minus this, you'd get a number close to 0, because this would be positive, this would be negative, this would be positive. We don't want that. We want all these numbers to be positive. So you'd have to split this integral up into regions. And that's what it says on this slide. So the symbols we use, it looks the same as what we just saw, except you have to put everything in absolute value. And the absolute value symbol tells us that the area must be positive. So even if you compute it and it comes out negative, doesn't matter, make it positive. So if the curves cross, the region must be broken into subregions and the areas summed. So let's see how to do that. So we're going to find the area of the region enclosed by y equals sine x. That should be y equals cosine 2x. That should be a y. That's a goof. I'll fix it before I post the PowerPoints. Yeah, it's y equals sine x, y equals cosine x. So from the graph, we can see that in the first subinterval, so here's our first subinterval, cosine 2x is on top, and sine x is on the bottom. Then we have a cross, and then in the second subinterval, sine x is above, and cosine 2x is on the bottom. So we write it out just as an ordinary integral. We just have to remember that where the functions cross, we have to split the integral into two, and we have to switch the order of the functions. So in our first subinterval, it'll be cosine 2x minus sine x, and our second subinterval, it'll be sine x minus cosine 2x. The other thing to bring up is that, again, I used Desmos for this, very accurate graph. You can clearly see it intersects at pi over 6, 1/2. But you may be asked on different problems or on the homework to do this by hand. Make sure you can do this by hand. So you know the answer if you want to try it, if you want to pause the video and try it. So this is how we write it. We're going from 0 to pi over 2, and we're taking the absolute value of sine x minus cosine 2x. When you write this out, it doesn't matter which one is first, because for one region, one of the functions is first. For the other region, the other one's first. So the order doesn't matter here. So then I split it into two. In the first subregion, from 0 to pi over 6, cosine 2x was the top function, and I'm subtracting sine x. Then I add that to the second subregion, which is from pi over 6 to pi over 2, where sine x is the top function. And then you just evaluate these two functions separately. So let's do the first integral first. Right, so this first part, this is a u substitution here. So if you need to verify that that is in fact the integral, go ahead and pause the video and verify it, but that is the integral. So I'm just evaluating this from 0 to pi over 6. Not tough to do. Just plug in pi over 6, plug in 0. Now what's interesting about this problem, and you're going to see it when you see the overall final answer here, this is just the area of the first subregion, is that when you're doing homework problems and most of the exams that you're going to take, I will ask for a exact answer. This is considered an exact answer. So I'll explain that more on the next slide. But again, if you're working it out at home, make sure you're showing all the steps. you know, and keeping track of the negatives and all that little bookkeeping stuff that you need for a class like Calc 2. Now here's our second integral, right? The second half here. It's this one. We're going from pi over 6 to pi over 2. Again, same sort of u substitution thing here. Evaluate, plug in pi over 2, plug in pi over 6. Get exact values. So we had the first function, the first integral had an answer for it. Here's the second integral. So we have two regions. Both of these are positive numbers, so we add them together. So here's the first region, here's the second region, and when you add it together, you get this. And that's an exact value. Some of you may be tempted to, as I'm going to show you here real soon, you can do definite integrals on your calculator. The homework will not accept this. On a test, you are going to have to give exact values unless otherwise specified. So you'd have to do all of the arithmetic here. The homework needs exact values, and on an exam I need them. So you're going to have to be able to work through problems like this. So if a problem like this one makes you nervous, pause the video and try it again and see if you can do it. So here we go. Last thing we're going to talk about today. Unless you're watching a bunch of videos all in one day. Definite integrals on a graphing calculator. So I put all the steps in the PowerPoints. If you've looked through the PowerPoints, you saw it. And it turns out most graphing calculators will compute definite integrals. All the TI series will. And some will compute indefinite integrals as well. So the more advanced Inspires and stuff like that will. There's also computer algebra systems. So that's things like MATLAB, Mathematica, and such that are computer programs that are fully developed to do all kinds of mathematical processing. And then there's online services such as wolframalpha.com. I told you in the syllabus that Wolfram Alpha is allowed to be used in this course. You just have to be really careful. Whenever you are working with something that gives you answers for free, you should probably verify that you can do it by hand before you just start getting free answers. But I do want you to be able to check your answers. So that's why I'm giving you the opportunity to do definite integrals in the calculator and telling you things like about Desmos and Wolfram Alpha and stuff like that. So the steps are listed below. I'm going to go ahead and just go to the example because the steps are built into the example. But if you need a reference, there's your reference slide right there. All right, so we're going to do example 1 again using the graphing calculator. So there's example 1. So the way you do it is you go to the y equals and you just type in the function just like you were going to graph it. In fact, we are going to graph it. But I'm going to show you a special way to graph it that some of you might not know about. And this usually works for graphing functions. Then go to Window and input the values of the limits of integration as x min and x max. So for this problem, for the integral we're doing an example for, we were integrating from 0 to 6. So you plug in x minimum is 0, x maximum is 6. The rest of it, don't worry about. We'll deal with the rest of it later. Just put in 0 and 6. So if you want to work through this with me right now, just go ahead and pause the video. But I'm going to keep going. Then you go to the zoom and you scroll down to zoom fit. It's on a TI-84, it's number 0. And then you're going to select zoom fit and you're going to hit enter. And then once you hit enter, it'll draw the graph. Then once you have the graph drawn, go to second table. It'll give you this calc function here. It's right next to F4. Scroll down and select integral f of x dx. Press enter. That command, once you have the graph drawn, that command, you put in values of x and it finds the definite integral. It finds the area under that function. So type in the lower limit. So for this problem, we were going from 0 to 6. Just type in 0, press enter, and then our upper limit is 6. Type in 6. For your upper limit, hit enter, and then it'll fill in the graph, and it'll give you the answer right here. And we already did this problem, so we know the answer is 36. So once you've done this a couple of times, it's really easy to do, and it's a good way to check answers once you get like the integral set up. You can just do this and see what the answer is. And if you want to try working through it by hand, again, a lot of these you're going to have to work through by hand if it's an exact value, but you can always just type in that exact value and check it and see if the answer is right. So it's a good way to check answers, especially for the longer problems that are really hard to do. All right, well, that's it. Last thing I want to say before we exit the video is that in general, exam problems are not to be solved with the cheating method on the graphing calculator, but I might give you specific instructions on an exam. I might say something like set up the definite integral, and then I might say something like evaluate the definite integral using your calculator. So if you want to do it by hand, that's fine. If you want to do it on the calculator, that's fine. But it still is a very handy tool for checking answers no matter what. All right, so there is a lot of extra stuff, obviously, in the ebook that you can check out. Chapter 5 is very, very visual, so any of the extra like graph manipulation things that are in the Explorits are very helpful. And as always, check out the online resources at the bottom. They're very, very good. Well, that's it for this video. I'll see you next time, and bye-bye.